Hello, everybody. Welcome to our CMI webinar series designed for and by CMI. And welcome, it's the beginning of a new academic year. So many of you are academicians and we're so delighted to have you even in the hecticness of starting out the semester. Glad to have you here with us. I'm Cynthia Howell and I'm the Education Training and Outreach Manager for CMI, and I'm going to be your moderator today. I'd like to tell you a little bit about the webinar series for those of you that may not have been with us before. They are hosted by Colorado School of Mines, and we are always looking for webinar topics that will serve our Critical Materials Institute population. So if you have any ideas, please feel free to email us and or also make sure that you contact us by cmiaimslab.gov. This is a public webinar, and a recording is going to be available at the aimslab.gov/CMI under the workforce setting, and that will happen in about a week. Questions, we are taking questions through the Q&A process here on this webinar, and it does take a while to queue in your questions. So when you have one, go ahead and queue it in. The presenter would like for us to hold questions until the end, and at that time we will start answering them, but we certainly do appreciate having questions queued up. Now I'd like to take a few minutes to introduce our presenter today, Dr. John Sutherland. He's the head of environmental and ecological engineering at Purdue University. He received his BS, MS, and PhD degrees from the University of Illinois at Urbana-Champaign. Also, he is considered one of the world's leading authority on the application of sustainability principles to industrial issues. You'll learn a little bit more about that as he goes on in his series. He's an investigator on several projects that have been funded. He's worked with over 100 students and has nearly 400 papers with that group of professionals that he's been working with over time. What I'd like to do right now is not take any more time from John, and may I have you take this series over.
Thank you very much, Cynthia.
You're welcome.
Hopefully everyone can see the screen okay and hear me okay. So thank you all for joining me here today. It's my pleasure to talk a little bit today about kind of a follow-up seminar to what we discussed a while back. Today we'll be looking more in depth at fractional factorial designs. So let me just comment and note that in our previous webinar, we introduced design of experiments, and we talked a lot about 2 to the k factorial designs. Again, today we're going to be diving into the world of 2 to the k minus p designs. We'll spend some time today talking about a little bit about the motivation and fundamentals associated with the designs, how we step through creating such designs, selecting generators. Then we'll look at a kind of non-specific to CMI example case study focused on something that sounds delicious, soybean whip topping, and wrap up with a little summary and hopefully have some time for Q&A. So let's spend a little bit of time talking about what the motivation is for fractional factorials. Let's consider a case where we're interested in investigating some phenomenon, and maybe at the outset we identify 10 variables that we believe could be important. If we were to consider those 10 variables in a full factorial, that's over 1,000 tests, 1,000 experiments that we would have to conduct, which is a lot. We get a lot of information, information on the mean, 10 main effects, a number of 2-factor interactions. You can actually calculate the number of each type of interaction down here. It's essentially the number of combinations of variables considered in groups. And it turns out that as we consider more and more experiments in a situation like this, where we're considering all possible combinations of the variables at 2 levels, the fraction of the total important variables is going to become smaller and smaller as we consider more and more variables. As the order, the number of variables considered grows larger, the fraction of variables or the fraction of effects that are significant becomes smaller and smaller. We refer to this as the sparsity of variable effects. So maybe if we were to conduct a 2 to the 10th full factorial, maybe only 20 of the effects would be significant. So we start thinking, is there a way to examine all these variables and maybe not have to consider so many tests? Can we look at a smaller set of tests and get nearly the same amount of information? And that's really the motivation for fractional factorials. So we're going today to talk about 2 to the k-p fractional factorials, some quick nomenclature. They're k minus p, couple things. The 2 is the number of levels for each variable that we consider. K, in this case, for this example, is 5. So that's the total number of variables we're investigating. If you look at 5 minus 2, that's 3. So 2 cubed, that's 8. That is the number of actual tests that we're going to run. The way that we're going to consider 5 variables and 8 tests without having to consider all 32 tests, that would be the case for a full factorial, is we're going to introduce these two variables into what we call the base design. And fractional factorials are a great way to start out an investigation. It's a way to efficiently examine many variables with a small number of tests. So let's consider this 2 to the 5 minus 2 fractional factorial design. I mentioned that the base design has 8 tests. Here are those 8 tests in 3 variables. It's a 2 cube base design. As we learned in our last webinar, we can write out using the alternating plus and minus signs or minus and plus signs in the one column. Here we have column 2 in groups of 2 minuses, 2 pluses, 3. So this is all possible combinations of these 3 variables in these 8 tests. Our goal here is to try to introduce variables 4 and 5 into this, or in addition to these first 3 variables. So the base design, just as a definition, is the full factorial design associated with the number of tests that we wish to run. All right, and as I noted, our challenge here is how to introduce the minuses and pluses in columns 4 and 5. So what we're going to do is we're going to use a step-by-step approach. We know we need to introduce 2 additional variables, variables 4 and 5. And I've written out here what we called last time the calculation matrix for this full factorial design. Notice we have a column I, columns for variables 1, 2, and 3, and then all the possible interaction columns, 1, 2, 1, 3, 2, 3, 1, 2, 3. And again, just as a reminder, we obtained the signs for these columns by multiplying columns 1 and 2, 1 and 3, 2 and 3, and then all columns together, 1, 2, and 3. So what we're going to do is, just for now, we're going to say, let's use the signs in the column 1, 2 to introduce variable 4, and the signs in column 1, 3 to introduce variable 5. And we'll see what that gets us. One other thing before we move on from this slide, I'll just note here that if I take any column in this calculation matrix and I multiply it times the I column, so in other words, if I take column 1 and I multiply it times I, I'm going to get back column 1. Second thing, if I take column 1 and I multiply it times itself, so in other words, column 1 times column 1, minus times a minus will be a plus, plus times plus will be a plus, minus times minus will be a plus, and so forth. So any column times itself will give me column I. All right. So I said that what we're going to do is introduce variables 4 and 5 using column 1, 2 and column 1 and 1, 3. And just using some symbolic nomenclature here, note that column 4, I'm introducing that by using column 1, 2. And variable 5, I'm introducing that using column 1, 3. So if column 4, variable 4 is equal to 1, 2, then I can multiply both sides of that relation by 4. And so column 4 times column 4 is going to be column I, and column 1, 2 times column 4 will be 1, 2, 4. So here's another way of writing out this 4 equals 1, 2 assignment. Similarly, for column 5, multiply both sides by, or variable 5, multiply both sides of this relation by 5, I get I equals 1, 3, 5. So what we can say that we're doing here is we're introducing variable 4 through interaction 1, 2, and variable 5 through interaction 1, 3. We are deliberately confounding variable 4 with the interaction 1, 2, and similarly for variable 5. We say that these are the generators for this fractional factorial design, this specific fractional factorial design. Another way of expressing the design generators is with this alternative form, I equals 1, 2, 4, and I equals 1, 3, 5. So now I have signs for each of my 5 variables in 8 tests. This is my 2 to the k minus p, 2 to the 5 minus 2 fractional factorial design. With this information in hand, and we know, of course, that these minuses and pluses correspond to actual levels for these variables, I can now go out and run my experiment. So this information in this matrix here, we could think of it as a design matrix, allows me to conduct my experiment, my fractional factorial experiment. We also sometimes call this the recipe matrix because it has the recipes for each of the tests in the experiment. So for example, for test number 5, variable 1 is at the low level, 2 is at the low level, 3 is at the high level, 4 is at the high level, but 5 is at the low level. So with this information in hand, I can now go out and run my experiment and obtain my responses. All right, so because of the way that we've introduced these new variables, there are some additional things we need to consider. We've confused or confounded some of these interactions. So we want to completely understand what that confounding or what that confusing structure looks like. So let's try to understand that. So just to remind you, our design generators are listed. If in fact I is equal to 1, 2, 4, or 1, 2, 4 is equal to I, and 1, 3, 5 is equal to I, then their product must also equal I, and therefore this 4-factor interaction, 2, 3, 4, 5, also equals I. So this set of things that are equal to I is referred to as the defining relation for this 2 to the 5 minus 2 fractional factorial design. All right, so I actually is equal to 1, 2, 4, 1, 3, 5, and 2, 3, 4, 5. So those 3 products are all equal to I. Now, in general, that defining relation consists of all the words that are equal to I. And in this case, I have 2 generators, and for my fractional factorial design, the number of words in the defining relation, the number of things that are equal to I is equal to 2 to the p. So the way that we find what those are is we list them out, all the things that are directly equal to I, then we consider the generators 2 at a time, 3 at a time, 4 at a time, all the way up to p at a time. And in this case, for my defining relation over here, there are 4 words in the defining relation because p is equal to 2. If I had, for example, a more complicated fractional factorial, 2 to the 11 minus 7, for example, there would be 2 to the 7th words in the defining relation. All right, so how do we use this information? Let me come back here and just say one other thing. The length of the shortest word in the defining relation, and I'll come back to this in a minute, is termed the design resolution. So in this case, we note here that apart from I, the shortest word, the length of the shortest word in this defining relation is 3. All right. So here's the base design. That has all the columns that I can consider in 8 tests, all the possible combinations of pluses and minuses for my base design full factorial. Any other column that I could consider in these 5 variables, maybe 3, 4 or 1, 2, 3, 5, is going to correspond to one of these things. So there's only 8 columns that are unique. And so we saw that these 3 things were equal to I. It turns out that any other possible combination of the 5 variables, 3, 4, 1, 2, 3, 5, 1, 2, 3, 4, 5, 1, 3, 4, they're all going to be equal to one of these columns. So I'm going to get a whole confounding pattern associated with my 2 to the k minus p, my 2 to the 5 minus 2 fractional factorial. So for example, if I wanted to figure out what columns are going to be equal to 1, what effects are going to be equal to variable 1, in other words, this minus plus, the way to do that is to take that column 1, this header for this column here, and multiply it times each word in the defining relation. So if I take 1 and I multiply it by I get a 1. If I multiply 1 by 1, 2, 4, the 1's cancel because that's the way a column times a column times itself is going to be equal to I. So then I have I times 1, 2, 4. So that'll be 2, 4. 1 times 1, 3, 5 gives you 1, 3, or 3, 5, and then 1 times 2, 3, 4, 5 will give me 1, 2, 3, 4, 5. So here we can see all the effects that are equal to column 1 or variable 1. I've listed out this confounding pattern here in the yellow box. That shows me or tells me which columns are equal to one another. So if I only run 8 tests, I'm only going to get 8 unique pieces of information, and I'm going to get this confounding pattern that corresponds to these 8 things that I can calculate. Now, we might think, well, I've lost some information, but we'll see, maybe we haven't. All right. All right. One other thing before we kind of move on here and start trying to use this in a little example is I want everyone to try to recall what we talked about last time when we calculated effects. So I'll just remind you that when we had our effect calculation matrix or calculation matrix last time, maybe I had column 1, 2, and it looked something like this. What we did was we took that column of plus and minus signs, multiplied it times the responses, and we got an effect. We got a calculated thing, calculated number, and we called it E12. That effect, we said, was an estimate of the true but unknown mean effect of variable 1, 2. All right. So essentially, when we conduct our experiment, what we're doing is we're getting an effect that's drawn from a distribution, a normal distribution that's centered at mu sub EI, in this case, mu sub E12. All right. We rerun the experiment, we're going to get another value drawn from this distribution. And what we end up having to do is trying to determine whether or not this mean here is equal to 0 or indistinguishable from 0, or whether we have strong evidence that it in fact is something other than 0. So now when we do our fractional factorial, we want to do a similar thing. We want to calculate some effects or whatever we want to call them. We do have columns of plus and minus signs in our base design calculation matrix. Recall that is this thing. We have 8 unique things that we can calculate. All right. And we're going to be able to use those signs, apply them to the responses, and we're going to get a number. So from our base design calculation matrix, we're going to have our plus and minus signs. We can apply them to the responses, and we're going to get a number. But we don't want to call it E12 because previously, when we talked about full factorials, we know that there was this direct correspondence between the E's and the mu's. All right. And we don't have that now because we have this confounding among the effects. All right. So we're going to need some other way to refer to it. So we're going to call these calculated E's L's. All right. L stands for linear combinations of confounded effects. So I'm going to have an L associated with each column in that base design calculation matrix. And so let's say that I calculate a number associated with column 1, 2. I'm going to refer to that number as L12. All right. Now, the only thing that we have to worry about is just what exactly is that L12 telling us? We do know that column 1, 2 for our little example was confounded with variable 4, with interaction 2, 3, 5, and with interaction 1, 3, 4, 5. So when I calculate L12, what is it estimating? Is it estimating 1, 2, or 4, or 2, 3, 5, or some combination? Well, in fact, it's estimating some combination. So that L, when I calculate an L, it's estimating the sum of all those mu's associated with that column of plus and minus signs, that singular column plus and minus signs. So in this case, for our an example, if I was to calculate L1, it's giving me an estimate of mu of E1 plus mu of E24 plus mu of E35 plus mu of E1, 2, 3, 4, 5. Now, some of these may be 0. And as we noted earlier, if we're talking about high interaction effects that have a lot of variables associated with them, it's less and less likely that those are going to be important. So very often main effects are important, or 2-factor interactions are important. But as we consider 3 and 4 and 5-factor interactions, they're less and less likely to be significant. So our calculated value, RL, is in fact an estimate of a linear combination of confounded effects. In this case, it's actually a sum of confounded effects. So for our little example, our 2 to the 5 minus 2, I've written out the complete confounding structure here. L1 is giving us an estimate of these 4 mu's: mu of 1, mu of 2, 4, mu of 3, 5, mu of 1, 2, 3, 4, 5. Because it gets a little cumbersome to deal with the mu's and then the subscript E and then the subscript on each E, I've just dropped the mu E's, but please understand that these are these numbers here, these symbolic numbers correspond to the means. All right, now, when I look at this structure, based on what I just said about 3-factor and higher order interactions perhaps being negligible, if under that assumption, we can make that assumption and it's reasonable, then our confounding structure simplifies to that shown here on the right. And all of a sudden, what I thought was really kind of a messed up, confounded mess becomes a little bit simpler, all right? So I mentioned design resolution. The design resolution is, again, the length of the shortest word in the defining relation. For our little example here, it was resolution 3. Here you can see what the meaning of these different design resolutions are. If we, for example, have a 2 to the 5 minus 1 design, this just shows why it's important to think about the design resolution. If the base design is a 2 to the 4th factorial, which is the case for 2 to the 5 minus 1, I have a lot of choices in terms of what I can use for how to introduce variable number 5. So base design is 2 to the 4th, and I could introduce variable 5 using any one of these columns. So I could introduce variable 5 using the 1, 2, 3 interaction. And if I do that, I get a resolution 4 design. That means that 1-factor and 3-factor interaction are going to be confounded with one another, and 2-factor interaction effects are going to be confounded with each other. So that's one option, but I could also introduce variable 5 through a 4-factor interaction, which would give me a resolution 5 design. And that basically means that the 2-factor and 3-factor interaction effects are going to be confounded with one another. So note here that the resolution means basically 1 plus 2 is 3, 1 plus 3 is 4, or 2 plus 2 is 4, 1 plus 4 is 5, 2 plus 3 is 5, and so forth. So given these two situations here, which one is preferred? I think we probably all agree that we prefer the resolution 5 design, because that way, under the assumption that 3-factor and higher order interactions are negligible, we come up with kind of our confounding is greatly simplified. So this basically points out that there are kind of preferred generators. Here on this slide, I've listed some preferred generators. One of the things that, and the way it's set up is that there's different numbers of variables that we might be interested in. This is my textbook, for example, has a little bit bigger table. Here's the different design resolutions. If you, for example, consider a 2 to the 5 minus 2, one of the things you'll note there is that we can introduce variable 4 using either a positive for the assignment on 1, 2, or a negative on interaction 1, 2. Similarly with variable 5. So each one of these little cells here defines a family of generators. If you consider all the members of the family, you get the full factorial. All right. So this becomes kind of important because when we think about the sequential approach to experimentation, we may run some initial member of the family, and then we could follow that up with another member of the family to clear up some of the confounding. And I just noted here that when we use a different sign, we're basically just flipping the signs in the normal interaction column. All right, I want to leave some time here for a little case study. And as I promised, we're looking at a delicious example of soybean whip topping, non-dairy topping. The response in this case is the kind of the whippability. It's how fluffy this overall topping gets. You can see that there's 5 variables to be considered in this experiment. Lots of delicious variables that we're looking at. And the idea is that we're going to have a 2-cubed base design. So here you can see the base design column. These are the 8 unique columns, 8 tests. We're introducing 4 additional variables. So that means we have to use all of these interaction columns. So this is what we term a saturated fractional factorial. Can't study more than 7 variables in 8 tests. All right. So now we use the generators here, and here the recipe is written out for this 2 to the 7 minus 4. Here are the responses. I'll just note that because we have a 2 to the 7 minus 4, there are 4 generators, right? We have this for the defining relation. There's the 4 generators, and then we're going to have 4 choose 2. So that'll be what, 6 additional members, words in the defining relation, and we're going to have again 4 if we consider the generators 3 at a time. So we have to worry about the generators 1 at a time, 2 at a time, 3 at a time, and then all 4 at a time. The complete confounding structure is written down here. Kind of messy, but it's doable. And then if we kind of just then work to calculate, remember we've run this experiment, we can calculate our L's. This is what's associated with each of the L's. If I then kind of eliminate the 3-factor and higher order interactions, the confounding structure simplifies to this. And note here that this is in fact, as was promised, resolution 3 design because the main effects are confounded with two-factor interactions. All right. So when I use these responses in concert with these base design calculation matrix columns, so in other words, I take column 1, I apply it to the responses. Remember, you add everything up, sum everything up, divide by the number of plus signs. Here you can see I've calculated L1 for that. And that basically means that this number here estimates the mean of mu. It's mu of E1 plus mu of E24, mu of E35, mu of E67. Now, of course, some of these two-factor interactions and main effects could be 0. So I've constructed a normal probability plot here based on these effects. And here you can see that this group over here looks like it's not well described by this line that goes through the effects that are close to 0. The question is how to interpret this. Well, it could be that these main effects are all important, 1, 2, and 6, or it could be that interaction 1,7 is important, or 5,7 is important, or 3,5 is important. Could be lots of different explanations to try to interpret what's going on with the normal probability plot. So what we can do is run a few additional tests or one additional experiment to try to resolve some of this ambiguity. So what we're going to do is we're going to conduct, in this case, a mirror image design. There's other strategies that you could pursue. For example, if you felt like this was, some of these things was showing up because of the importance of variable 1, then you could consider a fold-over design that kind of unconfounds variable 1, 1, 4, and 1, 7. But in this case, mirror image design is a great way to try to separate out main effects from two-factor interactions. And we're going to talk about how to do that. So the idea with the mirror image design is to take our original recipe matrix and to flip all the signs from minus to plus and plus to minus to get a second recipe matrix. All right. So that's what I've done. Took all these plus and minus signs and flipped them all over here to get this design matrix, this new recipe matrix. All right. And went out and ran that experiment. Here are the responses. Now, what I don't know is I've clearly gotten another member from that family of generators that we talked about previously in that one table. So the idea is to look at this recipe matrix and reveal or uncover what were the specific generator assignments. So clearly 4 is still related to variable 1, 2, or the interaction 1, 2, but which is it equal to, is variable 4 or column 4 equal to plus 1, 2 or minus 1, 2? So it looks to me like 1, 2 here is plus, and that's a minus. 1, 2 here is a minus, and that's a plus. Minus and plus. So it looks like 4 is now equal to minus 1, 2. And 5 is equal to minus 1, 3. 6 is equal to minus 2, 3. And 7 is still equal to plus 1, 2, 3. So that's kind of the generator assignments that I've uncovered following this conduct of this mirror image design. So again, step through the design generators. Here's the new defining relation. Here's the confounding pattern. This is now all when I calculate my L's, I've now used L primes because they're all going to be a little bit different. When I do this, I have to, again, remember to be careful and work with the base design calculation matrix. All right. So when I calculate everything, I want to make sure that I get those assignments correct. All right. So here are the L's and what corresponds to the L's. And then here's what's the assignments associated with them. Again, to get those assignments, we're making the assumption that three-factor and higher order interactions are negligible. All right, so now what do we do? So I've got L's and L primes, and I've got things associated with each one of them. So what I can do is I can combine the results from my first design and then my mirror image design. So my first design, L1 was a number. It was estimating this. And mirror image design L1 prime was estimating this. If I combine the results by adding, these two-factor interactions cancel. If I do L1 minus L1 prime, my ones are going to cancel, my main effects are going to cancel, and I'm going to end up unconfounding this grouping of two-factor interactions. So that's what I've done to combine the results of these two designs. These results are shown here. I can put those on a normal probability plot. And so now what do I find? I find out that all these main effects are important, 1, 2, 4, and 6. But at this point, I've only run 16 tests, which is a lot easier than having to run 128, which I ran in the full factorial. So it's a much more efficient way of running experiments. Again, it's revealed the information in stages, it's a much safer strategy than running one large experiment. You'll notice here that I have this grouping of two-factor interactions that is also important. And in fact, you could run a few more tests to even unconfound these and reveal what's going on here. It's likely that this is important because of the 1-2 interaction. All right, so let me quickly summarize. And amazingly, this is about 35 minutes. We've covered a tremendous amount of information today. Just remind you that fractional factorial designers are excellent for getting started with an investigation of some phenomenon. Great for kind of whittling down which variables are important from a large set. We have seen that the power of running experiments and acquiring information in a sequential manner, gradually learning about whatever it is we're studying. In this case, we've shown how we can run one experiment and then combine those results with a second to provide a clearer picture of what's going on. We're always happy to work with you, both us at Purdue as well as our colleagues at the University of Arizona, help you with your experiments. I mentioned the textbook. Here is that. And I'd like to thank the Critical Materials Institute, which we all know about. And big thanks to Jesus Perez Cardona for his helping in working on these slides today. That concludes my presentation. Happy to address some of these questions.
Yeah, so before we get to start on questions, John, I wanted to thank you so much for a great presentation. It was just really interesting to hear about this experimental design with the fractional factorial designs. And also in the end, you just really made it very simple. It's like, well, instead of running 8 tests, we're running 8 tests instead of 32. Or as in the sample, we're running 16 tests versus 148. I think everybody's ears pop up, especially when you're running experiments and research. So thank you for presenting this, for giving everybody an idea of the expertise that you have. And we appreciate also that you said you're happy to work with the planning and interpreting experiments for our CMI body. So thank you so much for that. And it looks like we have 3 questions queued up already. So if you'd like to get started with those.
Yeah, we got a couple great questions from Eric. And I'll give you my Eric Schwegler. So first question is, in practice, do you ever use more than 2 levels? If I'm just starting out investigating something, I'm only looking at 2 levels. I'm not sure whether if, for example, if I'm like the soybean whip topping, it turns out that 3 of the variables weren't important at all. So when you pick lots of levels, it tends to drive up the experimental effort. So I would start out at 2 levels. You can always go back and add a 3rd or a 4th. So that's question 1. Question 2 from Eric Schwegler is, does it matter which variables you select for P and which you select for K? So the variables that you're going to introduce into the through the generators, it may be, and we used to get exam questions like this in my design of experiments class, it may be that some specific combinations of variables are difficult to run, and that might dictate what you do in terms of picking specific generators. If you go back to that recipe matrix, though, Eric, you could pick any 3 columns and get a base design from that. So to some extent, what's in the base design or not in the base design is arbitrary, but the specific generators that you pick, likely there could be some sensitivity there, and you might need to make some judicious choices. And then Hongyue Jin has a question. Thank you for the nice presentation. Oh, you're very nice, Hongyue. Thank you. Could you comment about using fractional factorial design for process optimization? So again, I like to think about experiments in acquiring information in kind of an evolutionary, iterative fashion. If I'm just getting going and don't know what variables are important, don't know too much about the phenomenon under study, I want to have a highly fractionated experiment where I'm not wasting time investigating variables that I don't know whether or not they're important. As I acquire more information, I might begin thinking about process optimization, in which case you can always complement a fractional factorial with additional tests to begin thinking about process optimization. Hopefully that answers the question. You knew that answer anyway, so but it was good. I'm glad you asked it. So here's a question from Zachary Crandall. Does any software exist to aid in this type of fractional factorial design? You know, there's numbers that there's software that can be used to crunch the numbers. I'm less familiar with software that's out there that can reveal some of the the defining relation and confounding patterns. We had some software that worked in the 80s, but I don't think, Zachary, that it's likely to work anymore. So it's a good question. Maybe we should suggest that to Tom LaGrasso. But
Good point there. I love it. We've got a little bit more time. So while we're waiting for another question or two, I again wanted to thank you for opening up this expertise to the CMI body. And obviously you can see that there's some interest there. At this point, is there anything else that you'd like to say about this experimental design to add to the conversation?
No, again, you know, the last webinar we gave broad introduction to design of experiments, emphasis on 2 to the K full factorial designs. But most of the time when we start an investigation, we start with fractional factorials. Our hope is that we can have a future webinar that gets into the issue raised by Professor Jin, looking at process optimization and response surface methodology and higher order designs and in fact models. So here's another question from Eric.
Great, thank you. Another question.
Can you mention some of the CMI projects that you have done this for? Hongyue has, Dr. Jin has worked on some. I'm trying to remember. We've done some in a, and I'll just, you know, let me take a step back, Eric. So one of the reasons that I encourage people to think about design of experiments is that oftentimes over the years, people will come to me after they've conducted the experiment and they need help interpreting the results. And unfortunately, they very often, their first step was to go to somebody in the statistics department who are very knowledgeable individuals, but they don't always think about the experimental effort. And so I want to make sure that we're being wise with our resources and not out there conducting 1,024 tests when we could have gotten the same information from, you know, a much more efficient experiment. Here's a question from David Reed. Yeah, so actually the soybean whip topping did result in fluffier topping. You know, this is why we have such a in part such an abundance of soybeans growing out there. I also note that I did some work on healthy hot dogs, and I didn't actually have any of those healthy hot dogs. So yeah, the lithium ion battery recycling experiment, that was the one that remind me, Eric. So Eric's question was about the lithium ion batteries recycling. Was that the one that City worked on? I can't recall. I may have to come back to that one. Then we have a question from Dr. Fujita. Can the analysis indicate whether variables that you thought were independent actually are not? So, so let me talk about that. So when you conduct designed experiments, there's always this assumption that you can control your independent variables. So we call them independent variables because we can manipulate them independent of one another. So I'm trying to understand exactly what you're asking. So we kind of go into the experiment thinking that the variables are independent. If we have a problem controlling the variables and independently manipulating them, then yeah, that's a concern. We'll probably have to address that some other way within the experiment.
Okay. All right. This is perfect timing right here. We don't have any other questions open. Don't hesitate to contact John via email with any additional questions. I want to thank you all again for attending, and this recording is going to be available next week at aimslab.gov/CMI. Again, remember that's under the workforce menu. Please join September 29th with Christopher Dale of Perpetual Resource will present for us, and we'll look forward to seeing you again at that point. Details are going to be forthcoming, and they'll be in the critical times as always, or at aimslab.gov/CMI, again, under the workforce menu. Please let us know if you have additional information about a topic that you'd like to see. And so the very last question was actually a big thank you from Eric. What a great way to end. See you again next webinar. Bye, everybody.